In part 1, we built the bending equation and we met the section modulus. Now we use them. This film is nothing but worked problems, the kind your paper actually asks, and you should have a pen in your hand. Here is the good news before we start. Every single problem in this topic, whatever the shape, follows the same 5 steps. Locate the neutral axis, find the second moment of area about it, find the distance to the extreme fiber. Divide to get the section modulus, then multiply by the permissible stress to get the moment the section can carry. 5 steps. Every time, everything that looks difficult later is only one of these 5 steps taking longer. Start with the simplest shape there is. A timber beam simply supported span 3 meters. The section is 120 millimeters wide and 180 deep. The permissible bending stress is 10 newtons per square millimeter. Find the safe load, step 1. The neutral axis. The section is symmetric, so it sits at mid-depth, 90 millimeters from either face, nothing to calculate. Step 2 and 3 together because for a rectangle we already know the answer. Z equals BD squared over 6, that is 120 times 180 squared over 6, which is 648,000 cubic millimeters. Step 5. The moment this section can carry is the permissible stress times Z. 10 times 648,000 is 6.48 times 10 to the 6th Newton millimeters, which is 6.48 kilonewton meters. Now the load, if it is a uniformly distributed load, the maximum moment is WL squared over 8, that is W times 9 over 8, which is 1.125 W. Set that equal to 6.48 and W is 5.76 kilonewtons per meter. But suppose instead it is a single point load, 1 meter from the left support. Then the maximum moment is PAB over L, that is P times 1 times 2 over 3, or 0.67 P, set that equal to 6.48, and P is 9.72 kilonewtons. Same section, same permissible stress, only the loading changed and with it the answer. Now a shape where students lose marks for a silly reason. A steel pipe, outer diameter 60 millimeters, wall thickness 8 millimeters. It spans 2 meters, simply supported and carries a point load at the center. Permissible stress 150, find the load. First, the inner diameter, and this is where the marks go. The wall is 8 millimeters thick on both sides, so you subtract it twice. 60 minus 2/8 is 44 millimeters, not 52. Now the second moment of area. For a hollow circle, you take the outer and subtract the inner pi over 64 times 60 to the 4th minus 44 to the 4th. That comes to 452,188 millimeters to the 4th. The extreme fiber is at the outside 30 millimeters. So Z is 452,188 over 30, 15,073 cubic millimeters. Moment capacity is 150 times that, 2.261 kilonewton meters, and for a central point load, the maximum moment is PL over 4, which is 0.5 P. So P is 4.52 kilonewtons. Notice the pattern for any hollow shape. Work out the whole solid section, work out the whole subtract. Never subtract the section moduli. Subtract the second moments of area first and divide at the end. Next, an eye section and a trick that will save you 5 minutes in an exam hall. A built-up eye, flanges 180 wide and 10 thick, overall depth 400, web 10 thick. It is a cantilever 2 meters long, permissible stress 150. Find the safe uniformly distributed load. Now the honest way to find I is 3 parallel axis terms, 2 flanges and a web. And it works, but it is slow and every term is a chance to slip. Here is the faster way and Bhavikati gives it himself. The section is symmetric. So imagine the full rectangle, 180 wide by 400 deep, and then cut out the 2 voids either side of the web. Each void is 85 wide and 380 deep, and together they are one rectangle 170 wide by 380 deep. So I is 1/12 times 180 times 400 cubed minus 1/12 times 170 times 380 cubed, that is 182.65 times 10 to the 6 millimeters to the 4th. One line, 2 terms. The extreme fiber is 200 millimeters. half the depth, so Z is 913,233 cubic millimeters. Capacity is 150 times that, 136.99 kilonewton meters. And for a cantilever with a uniformly distributed load, the maximum moment is WL squared over 2, not over 8. That is 2W, so W is 68.49 kilonewtons per meter. Watch that cantilever formula. Writing WL squared over 8 out of habit is one of the commonest errors in this whole topic. Everything so far had one thing in common. The section was symmetric about the neutral axis. So the neutral axis sat at mid-depth, and there was one distance to the extreme fiber and one section modulus. Now we cross into the second half of your syllabus, and none of that is true anymore. For a T-section or any built-up section, the centroid is not at mid-depth. And since the neutral axis passes through the centroid, as we proved in part 1, the neutral axis is not at mid-depth either. The top fiber and the bottom fiber are now at different distances. Different distances mean different stresses. And different stresses mean the section has two section moduli, not one. Here is the order of work, and it never varies. Split the section into rectangles. Locate the centroid from the bottom fiber. Apply the parallel axis theorem to get I about that centroid. Find both edge distances. Get both section moduli. Then decide which one governs. Here is the section: a flange 200, wide and 50 deep sitting on top, and a web 50 wide and 200 deep hanging below. Overall depth 250. It is a mild steel beam simply supported over 4 meters. Permissible stress 150 in both tension and compression. Step 1. Split it into two rectangles and tabulate. Always measure from the bottom fiber. It keeps every number positive and it removes sign errors, which is where most of the lost marks in this topic actually come from. The flange, its area is 200 times 50, 10,000 square millimeters. Its own centroid is halfway up the flange, and the flange sits on top of a 200 deep web, so it is 200 plus 25, 225 millimeters from the bottom. Area times distance is 2,250,000. The web, its area is 50 times 200, also 10,000 square millimeters. Its centroid is halfway up the web, 100 millimeters from the bottom. Area times distance 1 million, add them. Total area 20,000 square millimeters. Total first moment 3,250,000. And the centroid is the second divided by the first. 3,250,000 over 20,000, which is 162.5 millimeters from the bottom. That line is the neutral axis. Now, the second moment of area about that neutral axis by the parallel axis theorem. For each rectangle, take its own second moment about its own centroid, then add its area times the square of the distance from its centroid to the section centroid. And here something convenient happens. The flange centroid is at 225, the section centroid at 162.5, so the shift is 62.5. The web centroid is at 100 and the shift is again 62.5. Both parts the same shift. The flange gives 200 times 50 cubed over 12 plus 10,000 times 62.5 squared. That is 2,083,000 plus 39,062,041.15 times 10 to the 6th. The web gives 50 times 200 cubed over 12 plus the same 39 million, so 72.4 times 10 to the 6th. Add them. I is 113.54 times 10 to the 6 millimeters to the 4th. Now the two distances up to the top fiber, 250 minus 162.5, 87.5, down to the bottom fiber, 162.5, two section moduli. Z top is I over 87.5, 1.298 million. Z bottom is I over 162.5, 0.699 million. The bottom one is smaller. A smaller Z means a larger stress for the same moment, so the bottom fiber reaches the limit first and it governs. Capacity is 150 times 0.699 million. 104.81 kilonewton meters, and WL squared over 8 with L 4 meters is 2W. So the safe load is 52.4 kilonewtons per meter. Stop and look at what we just calculated, because the picture explains it better than the arithmetic. For the rectangle, the stress diagram was two equal triangles meeting at 0 on the neutral axis, the same peak at the top as at the bottom. For this T, the neutral axis sits high, close to the flange stress, is proportional to distance from the neutral axis. So the diagram is still two triangles meeting at 0, but they are not equal anymore. The short one up to the top fiber is only 87.5 deep. The long one down to the bottom fiber is 162.5, nearly twice as far. So the peak stress at the bottom is nearly twice the peak stress at the top. That is the whole reason the bottom governs. And if you can draw this diagram, you will never again have to remember which section modulus to use. The longer arm always carries the bigger stress. Now change one thing. Keep the section, keep the span, but make the beam cast iron instead of mild steel. Cast iron is weak in tension and strong in compression. Take the permissible stress in tension as 30 newtons per square millimeter and in compression as 90, 3 times as strong one way as the other. The beam is simply supported, so it sags, which means the bottom is in tension and the top is in compression. Now Bhavikati gives us the rule: when the permissible stresses differ, work out the moment capacity for each phase separately and report the lower of the two. So, the tension phase is the bottom, and the bottom has the smaller Z, 0.699 million. 30 times, that is 20.96 kilonewton meters. The compression phase is the top with the larger Z, 1.298 million. 90 times, that is 116.79 kilonewton meters. The lower of the two is 20.96. Tension governs and badly. The safe load drops to 10.48 kilonewtons per meter, 1/5 of what the same section carried in steel. Look at those two numbers again, 20.96 against 116.79. The compression phase is carrying less than 1/5 of what it could. All that capacity is being wasted because the weak phase, the tension phase, happens to be the one far from the neutral axis. So fix it, turn the section upside down, put the flange at the bottom. Nothing is added, nothing is spent, we simply cast it the other way up. Now the centroid is 87.5 millimeters from the bottom instead of 162.5. I is completely unchanged, 113.54 million, because we only turned it over. And the two section moduli simply swap. The bottom in tension now has the large Z, 1.298 million, so 30 times, that is 38.93 kilonewton meters. The top in compression has the small Z, so 90 times 0.699 million is 62.88. The lower is 38.93 and the safe load is 19.46 kilonewtons per meter. Compare that with 10.48. The same section, the same material, the same span turned upside down carries 86% more load. This is why a cast iron beam is always cast with its larger flange on the tension side, which for a simply supported beam means at the bottom. It is a favorite Viva question, and now you know the answer and the reason. Before we finish, the mistakes that actually cost marks in this topic, and every one of them has appeared in a paper. 1. Using I about the base of the section instead of about the centroid. The bending equation demands the centroidal axis always. 2. Quoting one section modulus when the section has two, or using the top one when the bottom one governs. 3 units. Mixing kilonewton meters with Newton millimeters. Every problem today needed a 10 to the 6th somewhere, and this single slip loses more marks than any concept in the chapter. 4. Writing WL squared over 8 for a cantilever, it is WL squared over 2. 5. Forgetting to subtract the wall thickness twice on a hollow section. And 6. Assuming the neutral axis is the axis of symmetry, it is the centroidal axis. For a rectangle, those are the same line, and for a T-section, they are not. So 5 steps every time. Neutral axis, IYZ, capacity. If the section is symmetric, you get 1Z. If it is not, you get 2, and the smaller one governs unless the permissible stresses differ, in which case you check both faces and report the lower. That is the whole of your Diploma 3.2. The study notes and the practice paper for this topic are on our Telegram channel, with all 5 of these problems worked out in full. If this helped, do subscribe. Next in this topic, shear stress in beams and the shear center. See you there.